Good afternoon, everybody. Just for context, I am a new PhD student at Joseph Urban and Emma Veuvers. And today I would like to talk to you about compression. So specifically compression for predicting a new proof state in ATPs and ITPs. So just for some context for the people who are not familiar, let's try to make this work. Yes, so let's talk about some work that has been done in 2003 by some people whose name I cannot pronounce in Amsterdam. Sorry? Okay. Right. So let's consider an arbitrary compressor C, and let's denote CS as the length of the compression of the string S. So this compressor can just be anything like zip or 7-zip or something crazy like that. And let's then consider two strings, S and T, and what happens if they share and if they don't share any information. So if S and T are completely the same, then you can consider that the concatenation of the string, of the two strings, will be approximately equal to the compression of the first string plus some small constant b, because you can encode T basically using the information that you already have from S plus some minor bits to encode if you want to duplicate it, right? And on the other hand, if S and T share no information, so that does not only mean that they are not equal, but that there's no substructure that contains any kind of information that they can share, then you can expect that the concatenation will just be the sum of the two compressions, right? Because you will not be able to reuse any information there. And it is this idea that you can use to find a distance metric. That is this distance metric. So this is the normalized compression distance. And the idea is to just take this term that concatenates the two strings, and then you normalize it by subtracting the smallest compressed string and then divide it by the longest compressed string. And this gives you a number between 0 and 1, and it makes sure that longer strings are not penalized and things like that. And these people below there have proved that under reasonable conditions for C, and then you should think about commutativity of strings, that under commutativity it compresses equally well and some other stuff like that, it's not that important. You can prove that the NCD approximates a distance metric, so that means that up to some logarithmic factor it will be a distance metric. So this is an interesting thing, especially if you go to the theory of Kolmogorov complexity. So let's first define what Kolmogorov complexity is precisely for people who don't know. So let P be a set of programs, the set of all programs in the programming language L. And then if X is a program of L, then we say that L of X is the evaluation of that program. Then we define Kolmogorov complexity of K as the minimum, the smallest program in S, such that if you execute it, it will evaluate to your string S. So that's basically the idea. So you must find the smallest program in your programming language that will decompress to the string you're searching for. And in a very specific sense, this means that it is the best compression you're ever going to get. And this is, of course, only of theoretical interest, because if you're going to try to actually find an algorithm for this K of S, then you will have to evaluate this L of P for every possible P, and that means that you have to solve the halting problem because some of these P's will not terminate, right? So this is completely unsightly. But from a theoretical standpoint, it is interesting because if you now consider this NCD of K, so this is exactly the same formula, but now with the Kolmogorov complexity, and you can actually prove that in some sense NCD K is the distance metric. And to make it more specific, with D we mean that it subsumes all other computable distance metrics. So if you have some distance metric D, and this distance metric is computable, then you can prove that for every two sets of strings, the NCD of these strings is smaller than the distance metric that we consider. Yes? This is common for rough complexity. Or am I missing something? Yes, so what I'm saying is right, so it's density of K. So and where K is the best compression you're ever gonna get, right? So that's the idea there. This is of course a technical statement, but you can understand this as if you have two strings S and T, then any feature you're gonna extract from this S and T, if you're gonna have distance metrics on these features, your NCD is always going to be better than the distance metrics of this feature. So in some sense, your NCD of K encompasses all of your distance metrics and all of your features, and it works on everything in theory. So if you actually were able to make this problem graph complexity, we would have solved AI and probably any other problem in the world. So I guess for our jobs, it's a good thing that we haven't. Because we can't do this common graph complexity, the only thing we can hope for is to use an existing compressor to. No, it's not trivial. No, so I cannot explain it.
I couldn't get the maximum divided by max.
Oh, you mean this thing?
No, I mean that's clear, but I mean the inequality.
This thing.
Yeah.
So
okay.
No, it's not trivial. This is a non-trivial result of these people. If you're interested. Yes.
Also confusing. It says the best metric, but the way you seem to define best is just smaller than intent. Can you just clarify that?
Yeah. So
I find it vaguely.
This is somewhat confusing. I agree. So it's smaller. It means that that if there is a feature in there that is similar to the feature in, if there's a feature in S that's similar to the same feature in T, then it will be smaller. Then it will be small, right? And the NCD will be even smaller. Smaller or equal. So in some strange sense, you need to get some intuition for this. But in some strange sense, it is better.
I mean, the best metric should be zero metric.
Yeah.
Yes, but you of course also need that is true. But if two features are completely dissimilar, you need to have them large, right?
Well, yeah, I'm saying the point is if you define best in terms of skill, the best the best metric.
Yeah, so it is true that this is fairly complicated. So if you're interested, read the second paper here. I can point it to you. It's fairly complicated, and I don't really have time to really explain it.
Also, zero isn't a metric.
No, right, it's not a metric.
That's
effectively.
I mean, NCD is going to be measured in bits.
Is it going to be what?
Measured in bits. When you talk about the length of P,
Yeah, so you can measure.
Take any computable metric and scale it down arbitrarily, and it's still computable. So there must be a scale factor hidden.
Yeah, there probably is. Yeah, so again, I cannot completely explain this to you. If you're really interested, read the paper. I'm not the right person to ask. I'm more interested in the practical application of this. Let's go to the practical implications. So one very important thing is here that in order to do this, you need to have no domain-specific knowledge, right? So you can basically take anything from any domain you want and you throw it in this compressor, and hopefully it will just work. So these people have previously done this on, for example, music, in which case you get music that is clustered by author, clustered by genre, and clusters by style. Well, that's the same thing, I guess. You can compress codes, in which case it's also author and programming language and programming style. And you can literature, which will also do author and the time frame in which it was written, and if it's fiction or non-fiction. And you can look at character recognition, in which case you will just get clusters of the same numbers and letters and stuff like that. So it really works. So and nobody is claiming that it works better than a domain-specific distance metric. So in these cases, they have used many compressors like zip that you have on your everyday computer, and it works well, but not necessarily as well as the best thing out there. But the nice thing is that you can just throw it in and it works, right? So my proposal is now to let's use this for theory proofing. And in some sense, it's a little bit different from what we have here, mainly because all these things have large files. So you can just throw in large files and it will have lots of stuff to work with and lots of stuff to compress. But in our case, we have just formulas, right? The formula is maybe 10, if you're really crazy, 100 characters long, but then you're about there, I would say. So compressors are not made for this, because they are made for compressing large things, right? Why would you compress a small thing? So there is a little bit of a problem there, that the mathematical statements are short. Well, I have two solutions for this. First is to use a specific compressor type, which is prediction by partial matching. This is basically the state of the art in compression. And what this does is, instead of taking, for example, all kinds of dictionaries and embedding it in the compressed files, such as zip does, what it does is when it compresses, it sees the compressed stream as it sees the string as a stream, and it will start with a model that tries to predict the next bit in the stream. So you start with the first bit, you try to predict it from an empty model, and if you're right, you will not put your bit in the output stream, and if you're wrong, you will put your bit in the output stream. And then you update your model with the bit you've seen in order to try to predict the next bit better. And you again try to predict the next bit, and then if it's wrong, you put it in. If it's not wrong, you leave it out. And what you end up with is basically a partial string of the input. And then when you want to decompress, you again start with, you do exactly the same process. You start with an empty model, try to predict the first string. If you're wrong, then the bit will already be in the compressed string, right? Because during compression you will also wrong. And then you update your model and you go on and you're able to completely reconstruct the string. And the nice thing about this is that you don't have some huge constant overhead. So we can compress small things without losing our resolution in some overhead or some stupid dictionary, because we need every bit we can get from the compression in order to do the comparison. So the second thing is, instead of using formulas, let's just try to compress proof states, right? Because then we have multiple formulas and we can make it everything longer, and hopefully we'll get even more resolution there. So what we've done as an experimental thing is taken the lean-cop prover with a dataset from TPTP, where some of these things can be proven in lean-cop, and this ends up in about 300,000 proof states. So lean-cop is basically some Tableau system. It's somewhat more complicated, but I'm going to consider it Tableau right now. And one proof state is represented by one path in the tree of the proof states. So this is the place where we want to do inference rule. And in addition, we have a set of formulas we can do inference with. And one of these formulas needs to be chosen, right? So either A, B, negative A, or C. So what we're going to do is we're going to take this path and this thing, and we're just going to put it in a string. So we're going to put this thing first, and then this thing second, and then this thing third, and then this whole thing behind it, and we're just going to, nothing fancy, just put it in. And then we're going to compare this to a whole database of trees. So our proof states, right, that we have previously recorded. And these proof states here all have, we already know which choice needs to be made, right? and we compare it to everything, and the proof set that is closest to what we have here will be chosen. Only if the inference that is chosen here is actually in this list. If it's not in the list, we'll move on to the next best one until we find one that is compatible with this list, right? So in principle, a really simple thing. The difficult thing is getting it through a compressor in a fast way, actually. And then the results are like this. So this shows the percentage of inference rules that were correctly predicted. So this line here is the random baseline, if you were to just completely random predict stuff. And this line here is the best case you could do. And this is not one, because the best case, it can be that you have to predict a literal that is actually not in your data set, right? That happens in about 20% of cases, actually, which is fairly large. But, well, that's just what the data set is like. And then you see that we are predicting the k nearest neighbors. So for k1, we are predicting that we are only considering the very best prediction. In this case, we get about 63%, which is about double than random, so it's not that bad, I would say. And it actually progresses pretty quickly to the best case. So I'm not unhappy about this, especially if you think that there's really no domain-specific engineering going on here. So I think it's nice. So let's zoom into this a little bit. So this is the same graph. I hope you can see. So the magenta here is the same thing as we saw before, but now a little bit zoomed in. And what I did is, so going back to the string, the interesting thing is that we can, in theory, just put this in any order, right? So what I did is, instead of going from the top to the bottom and putting it all in sequentially, I also just randomized the order of this. And in theory, it should provide almost the same compression, almost the same results, right? And I also put it, for example, in reverse. So that are the blue and the white and the yellow lines you see here. So they're slightly worse than the magenta, but it is almost nothing. So that shows that this system is really robust against any encoding of your proof set. You can basically throw it in whatever way you want, and it will kind of work. And then this green thing is basically a comparison to a feature-based prediction. So we take the formulas and we extract features of size 1 and 2, I believe. Am I correct in that?
Yeah, that's what
yes. And then we do a k-nearest neighbor prediction on that. And you see that it is about 5% better, which is slightly better, but if you consider that this is domain-specific knowledge and this is not, then I'm pretty happy about it, actually. And you see that if you go farther in this KNN, then you actually get better. So, well, to me it seems fairly good. So these are the experimental results. One problem is that the compression is, of course, fairly slow, so you can do about 30 to 40 compressions a second, which is for ATPs probably not entirely enough. And another problem is that you have no vector space here. So you just have distance metric, which means that in order to do a evaluation, you will have to really compare to everything that is in your database, which is, of course, horribly slow. So that's a problem. And what I'm proposing, so I have not implemented this, but what I'm proposing is to impose a lattice structure, an n-dimensional lattice structure on your distance metric. So the idea is to take every point in your database and to give it n neighbors. And the idea is that these neighbors need to be as far apart of each other as possible, while they are as close as possible to the thing you're connecting it to. So the idea then is that you get like an n-dimensional thing, because the n neighbors are as far away as possible as each other, so they're pushed in every direction, and and they are still close to the original point. So this is the formula that is supposed to encode this. So if you have a data set S, then you can have a power set that contains sets of size n. And then the outgoing arrows of any database, anything in your database, will be the set of size n. such that it minimizes this formula, and here it says you should maximize the distance between the thing in your set of end stuff, and here it says that you should minimize the things, the distance between the things in the set X and S. So that's the idea, and I think that if you can impose this, then what you can basically do is if you're searching for something in your database, then you start at a random point, and then you do a hill climbing algorithm to walk towards the best value. So I'm not sure if this will work, but I think it's an interesting approach to try. But I'm not sure if it will be fast enough. In conclusion, some pros. So there's no domain-specific knowledge required, which is, I think, very nice. You can just use it for whatever you want. The predictions are pretty quantitative, right? You use about 5%, and I think that if you did a little bit of engineering, you could get it better, although that goes kind of against the domain-specific knowledge thing, but okay. You might be able to try another compressor or something. It is robust against different representations, so you can do mindless things and you just throw it in and it works. Some cons, it is relatively slow, and I think it is too slow to use for ATPs, but ITPs may be possible. So I'm thinking to apply it maybe in settings such as the tactic tow system, because there are less things to compare against, and I think it may be interesting to try applying it over there. And there's no vector space, which makes it horribly slow, but at least I propose some solution to that, so it would be interesting in hearing what you guys think of that solution. Some ideas. So this PPM algorithm, this prediction by partial matching algorithm, it is only for strings, right? And what we have are trees. So it may be interesting to write a compressor that works specifically on trees. I think we may be able to enhance the compression significantly like that. And secondly, well, we can do this and then show Lasse thing, and I'm curious how that will evaluate. So I'm also very interested in any suggestions or things that you think are wrong or ideas or something like that. So this is very much a project proposal, so we've only done some very initial evaluation. So that's it.
Did you try to help somehow the compression by putting some, I don't know, special symbols to say now comes something on the path, or now comes some lemma, or something like that?
Right, so that could be tried, and I think it may work, but it kind of goes against the domain-specific knowledge thing, right? But yes, so what you're proposing is to put some bars in between these things or something. Right? Yeah, I have not tried it, but it would be interesting to do, I think. Yes.
So what's also the average size of the thing that you're trying to compress?
I think it's between 500 and 1,000 characters.
That's only for the path entities.
Yeah. So there are lots of names in there. So we're not talking about just variables with one character, right? There are all kinds of names, Starsky, blah blah blah, this that, numbers. It's all about all the definitions of the TPTP library are in there. That makes it long.
So what are you exactly putting in there? You're putting the path. So
yes.
And what else are you putting?
I'm putting a possible formats that you can do resolution with in there.
Just for the current branch, right?
Yeah, for the current branches. So you're not putting in an entire tree, just the current branch, right?
Okay.
And that's it.
That gives you 10,000 characters.
500 to 1,000.
That's okay. Okay.
I was wondering when you compared it with feature-based stuff, which kind of examples did you use for your experiment? Was it from one domain in TPTP, or were the examples from different domains?
That's probably something you can answer.
Because right? I mean, there's no structure in there. No.
So I planned to be silent about this, but there was a mistake by Lasse. It's not TPTP, it's MPTP. And so it's basically, we use the, let's say, 33,000 Mizar top level problems that we can solve with ATP, we minimize them. Then we run it with link up, I don't know, in like 10 seconds, 30 seconds, and we get something like 11,000 proofs, link up proofs out of that. So it's spread all across the Mizar library. So it's pretty different domains in terms of mathematics, but you could argue that it's still somewhat more similar to one another than the whole TPTP because it's done by the MPTP encoding. So you have these type guards, etc. So
this might be
yeah.
Which implementation of PPM are you using? Are there many different implementations?
Yeah, so that's a good question. The state of it, so PPM is really state of the art, right? So all of the compression challenges are being won by this. And if you try that, you will actually fail horribly because one compression will take days. So this will not work. So you need some stupid PPM actually. So these are hard to find. So this is actually some obscure GitHub version of some PPM that is used for teaching. So it is a minimal implementation. And the interesting thing is that this minimal implementation is actually still better than zip. So it's really a couple of maybe a couple of thousand lines, and they're able to win from zip, but they are very far from the best compression because it will just be too slow and use too much memory.
Any other questions?
I mean, it seems to be a revival of Tableau methods.
Yeah, you should give us a brief introduction to HyperTableau because like the slide which Lasse was showing with the state, I think we are all in these link-up based settings slightly unhappy that we are not capturing the whole Tableau. Yeah. We are just being lazy and capturing the current path. And it seems like you are claiming that in HyperTableau we are good with just one path.
I was saying in general, Tableau method seems to be well suited
for machine learning. Oh, definitely. The state in Tableau, like yesterday in yeah. yeah, I agree.
Did you try FreeSync also?
No, I didn't. Well, I tried it for in an experimental setting. Well, it was all experimental, but I tried to run some short strings to it. But it's just too bad on short strings. It will just blow up with some dictionary that is completely empty, and it really doesn't work. So I could try it, but actually writing the code to push things through the compressor is actually fairly difficult because you need it to be fast, right? So you cannot just go through command line. So this is a lot of work. So no, I did not. But I don't think it's that useful.
So since we have time, we could turn this a bit into a discussion and ask Christian, like, because one like sort of analogy would be to these compression-based things like Word2Vec, which are unsupervised, and basically train on a huge corpus to compress, right?
So actually, you can look at the recurrent neural networks as a compression method. So if you train, let's say, a next token prediction, then you could do arithmetic encoding. And actually, the best compressors are neural compressors nowadays for text. So that is a huge analogy. So actually, my question was regarding this that so you say it's like one of the advantages that it's a domain, not domain agnostic. And so what we found is that for all these text things, that the vocabulary that basically just like, so it's not compression based at all, but it's just bag of words. So it's bag of tokens. So it's like you just give it a set of tokens, like a sequence of tokens, and then it extracts features by itself in this agnostic manner. And for our use case, like when we did proof guidance, that worked surprisingly well. So that we haven't. So I'm not really sure that this kind of like three tree-based approach is any better than
maybe not.
doing like throwing into warp purpose and figure out that. So that's really like a few hours of work. So that might be another interesting, and that's fast because then you just run it and classify it.
Right.
Yeah, I think that's an exciting thing that you can have this kind of like mathematically grounded distance measure.
Yeah.
So maybe the next topic for discussion would be, so we had this back and forth with Lasse, whether you will benefit if you throw in a huge background knowledge, like if you will, let's say, train first on some database of these things, and then you do the compression, like modulo this train thing, and his answer is like Kolmogorov is the god, and it will do it for everything, right? And now the question is, like, should we let Kolmogorov figure it out without the background knowledge, or should we sort of factor in the fact that we are not in the Kolmogorov anywhere near to Kolmogorov, and should we sort of train it with the background knowledge and then do the compression metric, basically? Like what's?
Yeah, so actually I was thinking of exactly that you so one way to utilize this idea to train a recurrent neural network and then use it as a compressor, and if you have a very powerful recurrent neural network that could do matching like with attention mechanism that can do like far away matches, then it gets like much more algorithmic. It can capture all kinds of far away correlations in the data that compressors typically don't. So yeah, so I think that's an exciting thing, and also the other thing would be that I could even train a neural network to approximate this distance metric directly. So I'm not really sure that's but it would be a cool thing to see. And I mean, let's listen to the experiment.
So in some sense, this PPM, so this predictor, where you predict the bits, it is a neural network. So in some sense, this is all somewhat the same.
Yeah, but it's different if you compress and you directly just predict the distance that you don't have this. You don't have this division of the different things. But I would suspect that you need a special architecture for that because it has like there are two inputs to it and it has to somehow cope with that. But it could be that you create an embedding and then you try to approximate with a. So this metric could be approximated as a scalar product between two vectors, and the two vectors are computed by a neural network. So the stuff that you try to engineer, it could be generated by a neural network. But the reason I didn't ask that because it would be slower than the current than what you are proposing. So computing the features in the neural network is about so it's probably slower than this 30-40 lookup that you do by compressing. So and but you have added acceleration. So it might be faster than a year or nothing. Yeah. So but yeah. So any other ideas or contributions?
I guess it's not really the same subject matter to do with compression. It reminded me of Frank Villaine's De Bruijn factor, where he compares the length of informal and formal proofs. And he does this pre-processing step where he just feeds them both through GZIP. It's a very weak approximation of informational content. So it would be interesting to see if it had any, if these better compression methods have any contribution to make there, like as a metric for how close to an informal, or how complex proofs are relative to an informal text, or maybe how hard it is for tic-tac-toe to reproduce a good human proof. Maybe compressed length might turn out to be a good proxy for that.
Yeah, I think that in general, compression is a really interesting thing that we should really think about this as an analogy, right? In some sense, compression and interactive theorem proving is kind of the same thing, right? It's all about information and trying to predict stuff. And I think it's useful to look in both domains for ideas and things like that.
So actually, I think it has more chance. So I'm a huge fan of. In the past few months, I thought a lot about these things. And actually, you are right. So it's like it's absolutely the same. That say you have the formal and the informal proof, and then you say, I want to utilize the informal proof to find the formal proof more efficiently. So the guide the proofs. And then let's say I have a neural network that does the decisions, and if I feed in the informal proof as kind of like an embedding or side information to that network, then if I train that with a lot of informal proofs, then the neural network could extract those features from the informal proofs that have guiding its proof. And if that network is like a recurrent network or something, then it makes more precise decisions. That means it's a better compressor. So having a neural network making better decisions, that means that if you do arithmetic encoding on the choices, then you can you compress your proof better. Yes. So basically that's a measure of how useful that site information. So and that could be used for actually mining for informal theorem. So you say I have an initial model that can utilize informal a bit. And then you start doing sliding window on your data, and then you say feed in, and see which one helps most. That means which one compresses the best, like almost the same thing. And then you that way you can find matches for your proof. Maybe you find another proof that is similar, that it helps. But if you can look in your database and say, okay, I have a good retrieval system to find the right side information to throw in to accelerate my guidance, that could do have bootstrapping and informal to formal matching. So yeah, these are really exciting directions. I absolutely convinced that these things, and you could do the same with format.
Yeah, exactly.
So you have a bit like corpus of proofs, and then you feed in. So one could actually do that same with wizard and so it's like you say that I take the wizard text, and although I don't transform the truth into an ATP proof or a tactic or a whole proof, but you could guide, let's say, tactic with the wizard proof text if you have a higher or a whole reformulation of yeah.
It's unrelated, but do you think you could use this TPM compression to guide the discovery of certain domain-specific features to use without compression then?
So you want to randomly generate features or something and then try to see how good they are, or something like that?
I want to. This compression seems to be doing, in some ways, better than the unselected features.
Yes.
So could you use some compression schemes to get features out in some way?
Well,
you get features out of the compression scheme in some way?
So the compression scheme itself is basically a neural network that hand codes from features of mainly normal human text. And in that sense, you could look inside of the compressor to see what it's doing and why it's doing better than you are. That's definitely true. And what you could also try to do is maybe, well, I said if you generate features randomly and then see how good it compresses with the original, then you may be able to see like, oh, these features are good, these features are not good, something like that.
Okay, let's go for the last talk. So Olsak is going to talk about why we should care about gradient geometry.
very. I don't. Microphone.
You don't have that.
I mean,
I think it's better. You didn't use that.
no, I didn't.
So your speaker will be there again. Is this a bit higher? 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 Cannot take it higher. Or this. You can put it in your pockets.
All right. Thank you very much. It's a great honor to have the last talk AITP conference. On the other hand, it is the first talk about Euclidean geometry here. It's a bit pity, don't you think? So, uh, I start just by explaining what I imagine when I say Euclidean geometry. It's a simple theory about points and lines and circles in the plane. Here you can see an example of a theorem or problem or something like that. That if you take 3 points on a circle and then consider the bisector of the segment BC and the bisector of the angle at the vertex A, they will intersect on the circle. Well, and you probably met this topic on elementary school or high school, and you may remember your teachers forcing you to use the compass and the ruler. But then, when you look at the university, suddenly somehow nobody cares about this topic anymore, and I think that's mainly due to 2 reasons. That, of course, all these pictures are nice, but, well, there are no applications of it, neither in real world nor in other mathematical domains. And secondly, well, there are no interesting open problems in Euclidean geometry because you can just rewrite the constellation into algebraic equations and then somehow compute it, and that's it. So it's actually useless and trivial. But I hope that this is not what you will take from my talk, because I want to argue that despite its useless and trivial, it's actually an excellent topic for this conference. So, what I mean by this conference, I imagine, from what I understand, there are somehow two types of people. There are people that are experienced in automated theorem proving, and they would like to understand machine learning better. And then there are people experienced in machine learning, and they would like to understand automated theorem proving better. Well, I'm an exception. I don't understand neither of them deeply. So, in fact, I am a mathematician. I'm a PhD student in mathematics, and I'm trying to solve some problems that my supervisor gives me. These are my main problems from universal algebra. But because it's not always such a fun, I'm also dreaming that one day there will be the computer that will be able to do all the work for me. So I sometimes wonder what I actually want the computers to solve, what the mathematics is about, and I managed to come up with these three keywords. Well, I like the description of mathematics, that mathematics is somehow an abstraction of abstraction of abstraction, that somewhere deep in the deep there are the concrete things, but mathematics is on high level above it. And of course, if we stay at the ground, mathematics is definitely about reasoning and problem solving in general. So let's talk about abstraction. Well, due to Wikipedia, abstraction is a conceptual process where general rules and concepts are derived from the usage and classification of specific examples, literal, real, or concrete signifiers, first principles, or other methods. Well, that's a pretty abstract definition. And there are two approaches how to get the abstraction into the computer, which corresponds to the division of the people I outlined earlier. One approach is to for logician, abstraction is not such a big deal because he already works in so abstract formal world that is just some operation like replacing constants with variables, or even in whole language, the conception of lambda function is called lambda abstraction. So even though this formula for integral substitution is quite abstract, because not only the x and t and a and e can stand for any real number, but even this p and f can stand for any function, any differentiable function. That doesn't matter so much, while the computer knows how to handle it informally. So that's one approach to it. And then there is the second approach. What actually happens in abstraction, that you feed a neural network with plenty of something, say plenty of pictures of dogs, and then the neural net can somehow abstract in its mind what's the meaning of what's the common thing in all the pictures. I know that I'm a bit oversimplifying it, but that's the idea. And the issue is that these approaches are not very much compatible. And so, of course, the usual way to apply machine learning for automated theorem proving is a bit different. And that's that you try to teach the AI how the superformal world somehow works, or how people are encoding their thought into the superformal world. And I admit that this can work to some extent. I really think that it's a good way to try something, but it's still a bit unfair to the AI. Well, it doesn't have the semantics of it, and I think that it's really difficult just from the syntax somehow realize what's behind it, what's the semantics. So my first idea is to focus more on what are the elementary math topics. So let's look at the elementary school. What's here, and you can see arithmetic, people, pupils at the first grade are taught to add numbers and these things. And I think that there is already, it's actually learning to perform some algorithms, and there is already some AI research to learn to use neural nets to do that. Well, the neural nets are not very good at it, but neither people are, so well. But then there are the word problems popular on elementary school, and I think that there is a huge AI research about the natural language comprehension and these things. And then you can find Euclidean geometry. And I think that Euclidean geometry is actually great because all what you have are some pictures that you are trying to teach the kids how they look like and how to draw them. And this can be somehow, it's just one level of abstraction in the sense that you can just directly give these pictures to the neural net. And if I ask myself why Euclidean geometry is taught in the high school, I think that another great reason is that it somehow teaches reasoning, that there are simple proofs in Euclidean geometry of statements that are not obvious at the first glance, but the proofs are simple, direct. There is no much need for even case analysis. You don't need to prove by contradiction. So these are one of the reasons. All right, let's change the topic a bit for now, and let's talk about problem solving. Well, I just asked who can recognize this logo. Is there anybody? Well, this is the logo of International Mathematical Olympiad, and for me, International Mathematical Olympiad is the holy grail for problem solving. I think that if we manage to solve the entire IMO, we are 3 years from singularity. So, but we are not here yet. It's a prestigious competition for high school students, and there are actually, if you look what problems are on IMO, you can find 3 main domains which are circa equally represented. That's algebra, that's some stuff about real numbers. Then number theory, that's something with integers. Combinatorics, that can be anything with discrete structures, and I think that this is the most difficult topic for artificial intelligence. And then there is the Euclidean geometry. And of course, to solve the Euclidean geometry on IMO by artificial intelligence is difficult in the sense that if you want to do it in the human-like way. But of course, even the people don't go directly to IMO. They train during in national rounds and rounds for younger students and these things. So that means that you can find actually wide range of problems of various difficulty for Euclidean geometry, actually from elementary school to the IMO level. And I think that's great because then you can see the progress of the artificial intelligence on one topic. And then there's one more point about IMO. That the people at IMO are actually pretty clever, and you may own them in your research. And well, how to get IMO people to the research, or well, either you pay them a lot of money, or you impress them and offer some cooler research. So there is a plan. So let me dream again. Right? Again, a bit dream, but I think that's a bit more achievable. So let's imagine that we can really somehow solve the geometry in the human-like way and get to the level of the people on IMO or human exceed. And then we could actually even generate some programs using this artificial intelligence and get these programs to IMO and then send the IMO people message like, hello, IMO competitors. Do you remember the cool program number 5 with the S-rank square? Well, it was actually invented by our artificial intelligence, but we are not stopping here at geometry. Our goal is to solve the entire IMO. So be with it. Join us. Let's solve the problem solving. So no. Yeah, so let's recapitulate what what are the what are the advantages of Euclidean geometry. You can find a wide variety of problems of various difficulty levels from elementary school actually to IMO. It's relatively simple from the reasoning point of view, so it's suitable for various AI experiments. It's about concrete pictures, so you can use image processing for it, and then the humans doesn't have any advantage against the AI issue. And we can attract IMO people by solving it. And let me deal with the objection, with the initial objections. Well, it's useless, but it doesn't matter because solving Euclidean geometry is not the ultimate goal, but the goal is to develop the tools for problem solving, for artificial intelligence in problem solving. And well, it can be just calculated, but if we don't implement these calculations in the artificial intelligence, it will not do that. So we can just ignore the fact and try to do more human-like approach. And so now I think that you are curious what I actually suggest to do. Well, it's there are some I have lots of ideas, but there are some obvious things to do. First is that there are lots of problems, but I'm afraid that these problems or solutions are not in a computer readable form. So get them somehow formalize them and get them into the computer readable form or generate your own. I know some people who are trying to generate problems. And then I was also impressed by the AlphaZero stuff, so I think that the natural thing to try is to try some reinforcement learning to guide the picture or the structure or both to somehow solve the problems. And I would like to notice that not just the problems of the form prove something are important, but even problems of the kind you have a setup and you need to construct it, because sometimes even the problems to prove are of the form that you have the setup and it's not explicitly stated how to construct it. So So you need to somehow handle this kind of problems too. And I think that it is actually not just a problem of Euclidean geometry that we want to have the way to construct examples of. But I think that Euclidean geometry is a great starting point. And well, that's all for me. And I'm interested of what you think about it.
So discussion.
I just want to point out that being able to solve especially large problems in Euclidean geometry is both has extremely important practical applications and also very so I think that the reason that like Euclidean geometry is interesting not because it's easy and has no applications, it's interesting because it has a ton of extremely important applications and it's actually very hard to do this, like, all our problems. So, I mean, the problem is interesting in its own way.
So, so isn't it really hard to judge the solution? So once you get the solution, I think it boils down also that you haven't really specified what you mean by solving. So is it like
Okay, yeah. So what I mean by solving, well, when it's a proof problem, I think that there can be done some axiomatic system for that, and there are people who already done that. So that
so could you come here? It's like would be easier to hear. Yeah, it's really you are very soft.
So you mean, and then on IMO there are human judges who judge.
Yes, and it takes a long time to decide how many points each one take.
That's true. So that's tougher for artificial intelligence to get just partial score. But well, if you just solve the problem on IMO, you get 7 points. So I think that's the goal, getting the problem solved.
So, but what do you mean? So is it like you're producing a natural language output that the judge would score in 7 points, or is it like you formalize it and then create a formally verifiable proof in an axiom ITP?
Yeah, I mean that I use some kind of formal language for the proof, but something that's more simple than the general thing. General I don't know vocal or is a language.
So Norikara and Takuya Matsuzaki have actually, that's what Mirek is talking about, have formalized some of these IMO problems in sort of a higher order logic. So it's
it's not a question, but I feel like IMO is gonna be pretty good benchmark. I mean, case people.
So I still don't really get them. I would like to understand the vision of the whole thing. So would you tell what do you think your input would be? So your input is a natural language text, or it's also it's a formal representation of your problem?
I think that I don't need their natural language. Because mathematicians are rather thinking in pictures and in their intuitive ideas. So I think that the input could be partially just some formal thing. Somehow the formal graph that represents the setup of the picture. And then it can get even the picture as a hint what's all actually going on.
Okay, so can you repeat your question or comment?
It's a comment. I think IMO is going to be a really good benchmark. I mean, for CADE people are using TPTP, but who knows about TPTP? CADE people know.
Well, TPTP is a collection which Jeff has tried to get from all sorts of application areas, right? So IMO might actually, because Jeff got these problems from Noriko and Takuya, might already be included in TPTP these days.
But
like Jeff was extremely interested when they did it.
Science, many people don't know about TPTP, but if you talk about IMO, everybody at university heard about it.
Yeah.
And I think in terms of the Todai robot project led by Arako Arai, I think the biggest achievement or the best part about that project is to target that Todai, which is still pretty famous in Japan, but IMO is famous in the world. And in terms of community building, if you can achieve superhuman achievement at IMO, probably more people become interested in this topic.
Yeah, we could probably sell it to these big companies like DeepMind or whoever, like when they want some great breakthrough like beating Lee Sedol, right? So that now they could claim like we have beaten the best IMO mathematicians,
So
right?
my personal skepticism is that isn't it so that if you throw it into grub databases, then these things are like just get them out without any problem. Isn't it? So maybe you can encode all these things as grub-based problems, and then you just it's an idea that should think that so it's not just algorithmically solvable. These are practically solvable.
Yeah, so you mean that it's actually simple
even to the extent.
Even for so it would be great if it's simple. I'm not sure about it. Well, if it is simple, you can make it harder for the AI to solve by don't.
So I would be surprised if it's hard to organize.
Well, there's a big divide over whether the problems involve some notion of orientation. So if they don't involve order or orientation, generally, on a basis of Wu's method work quite well. But when orientation's involved, the method's usually quite a bit slower than the other methods. So I mean, there's a huge subset for which they do work well, but there is a class of problem for which they don't work so well. Maybe.
That's good to know. I didn't know. Okay, so Ramana.
Yeah, a couple of comments. One is if you say that if you don't program the AI with the program basis method or something like this, then it will have to solve the problem some other way. I don't think that's true. If you have a good AI, you should figure it out.
Well, if you make the AI that's capable of figure it out by itself, it's pretty good.
It might surprise you.
But the point is that you can implement algebraic manipulation to the computer, and then the algebraic manipulation is really easy for the computer.
Yeah.
If you don't do that, and you just want the AI to do it by itself, it's not trivial at all for it. Like it's not trivial for it to just add numbers.
Yeah. So the other thing I should say is that the IOI has also interesting problems, but they have the advantage that they are easy to grade. So you can generate scores very quickly for example.
Yeah, IOI is definitely too nice domain to do. And I haven't been there. I've been on ACM ICBC, which is another competition of that sort. And well, yeah, I would like to solve IOI and ACM ICBC, but I think that this is harder than solving geometry. Then solving programming problems is more similar to solving combinatorial problems on IMO, and that this is way harder than just solving geometry. That's why I
Also give you first.
So on the subject of finding an underlying wanted for this, whatever. There's a system from Jeremy Omega from a while back, confusingly called E, that tries to model more or less exactly this, right? So natural reasoning with in Euclidean geometry, including diagrams, done in a formal way. And I think it would be a really interesting natural setting to explore this in. If I remember right, there have been attempts to automate proofs in the system also. I don't think that they've gone particularly far. That would be German hobby guy. I can send you a link.
Okay.
Yeah. It's a shame also that Michael Beeson has left.
I think that
Yeah.
I think that there is somehow plenty of research scattered around the scientific world about Euclidean geometry, so that's one of the reasons of my talk, to somehow collect what has been already done.
Have you also looked at the mass handler examples?
What?
Mass handler, they start with grade 1. But I am always very advanced, but there's a much simpler entry point. I mean, in the same spirit, but much simpler examples. It's clear from the
Okay, so no,
it's an international, so there's a Wikipedia site about it. I just got aware of it because my son's now getting you can download the exercise sheets of the last years in different countries.
okay, so it's
There's also
a
German
teaching app or something.
No, it's a competition that starts with, let's say, first, second grade.
Yeah, I see.
And then you have lots of kind of text
Of course.
presented. It's got natural numbers, pictures about geometry, all kinds of simple amounts.
Yeah. This is try easy things first.
Also, alle Uhren auf der Geocode-Projekt sagt, Universität Hamburg mit dieselbe zu, das specifically was of formalizing Euclidean geometry with some a bit of machine learning and also link with GeoGebra. I think it's some pointers.
Okay, that's excellent. So please send the thing. Well, one of my ideas, what could be done about collecting data and this GeoGebra was that we could somehow create an online applet where we would be recording people how they are thinking about the Euclidean geometry. So if they already somehow connected formal proofs and GeoGebra, that would be great.
So okay, actually, I also wanted to this. I just talked to Mike Beeson the other day, and I suggested a project that was much more automatic. So I'm a big fan of self-plate. My aunt was the stack, and so one possible way would be that you have this like GeoGebra style program, and so but it's like you're scripting it with some simple script that like an abstract form, and then so if you look at a few images of where the lines go or how they intersect, then of course you can experimentally see that you can observe a lot of theorems of certain style, like okay, something on the same line, on the same circle, in some order, etc. So what my suggestion is that you could create a system where your reinforcement learning learns to explore the space of its geometric problems by itself, by observing the results,
yes.
And then try to come up with new theorems as we go. So the whole thing could be completely automatic.
I know about some people who are trying to discover geometric statements in this way, and I don't completely know how they are doing it, but I think that they are not using artificial intelligence very much. And well, one of the projects is called Discover, and pretty secretive. I asked them a few questions and they answered that it's not available for public. And then I have a friend, or well, students in Slovakia who is creating programs for IMO, and his bachelor thesis is about this kind of software, and he thinks that it's not easy at all to generate IMO-like program automatically, but if we could somehow put AI into it, it could help.
So actually there is so generative models are relatively new and exactly business also not so expert. And I think that there is a significant chance that you can do that automatically. I think that really interesting open question is that if you do that, you can make two alternative systems. That one system that is during the exploration, it uses the actual image as a guidance, and the second system we just use the experimental results as a kind of like a hint to whether the theorem is true or not. The question is your guidance better? So does it have the neural network to actually see the images? So that's a very easy hypothesis to test. You just run these things and then feed in the take-home the images, and if it has actually, and that exploration gives you more new theorems, then it looks like that looking at the images itself, otherwise it just might be able to argue by just the abstract description. So I'm completely, so I have no idea what to do. It's an exciting open question.
It's okay.
Yes?
Like some of these things have been tried, like there was this AM system, and there is this system called Graffiti by Feitlovich, which sort of has something like you are describing. It is a database of graphs, and it's sort of chasing their properties. So it's sort of like computing some chromatic number, blah blah. So it's sort of similar to observing the image and looking at the intersections like you are describing it. And then it's making conjectures, then it's making more general conjectures. And like some of them, they gave them, for example, to R-Dash, and R-Dash found them interesting and proved some of them, for example.
Yeah, I remember they used like linear programming to figure out inequalities between the different graph parameters.
Yeah, they had a couple of like pretty specific heuristics for this, but
I remember it was like around 2000 or so. I saw some talks then.
Yeah, and you could say that the Lennart's thing was also sort of similar. Like you have some concepts and you are filling some sort of examples and counterexamples and making some conjectures based on that. So it sounds to me that actually last year we had a talk on doing something like this in some fairly high level algebraic schemes, like you remember Andreas Holmström, like that look like they have some pretty decent database of some sort of invariance that they compute on top of some complicated mathematical functions, some schemes, and then they also have a conjecturing program based on that. So I think that this general approach that we have some examples.
It's like most other approaches didn't use like the current.
No. There were no neural networks involved. Yeah, absolutely.
It's a unique.
Yeah,
unique opportunity at this time.
Yeah, absolutely. Yeah.
To really go into again. That is much more to be done then.
Yeah.
So this is like it's a lot of manual engineering, but you cannot just throw the general.
Yeah, I agree.
And so. Any other?
Let's eat.
So I mean,
okay. We should thank Mirek. Also, thanks everybody for coming and for making very interesting, sometimes provocative talks. And please come again next year to Blaauwbroek and make equally interesting and provocative talks. That's it. Let's have a lunch.
You should thank the organizers.
Are those slides going to be systematically available? Or
Yeah, if you all send me the slides, then all the slides will be available.
What about the videos you've been making? Are those just like
Yeah, so if somebody strongly protests against having his video online, then okay, you take that, James. All right, and like whatever, if you are dissatisfied with the quality which will appear online, then you can also send me an email and tell me like this sucks too much, please.
Here's $500,000.
So in general, the camera, either I don't know how to do it, or the camera is too weak to capture those slides, which are there. So it needs to be mixed with your slides, basically.
But will it be somewhere obvious on the conference website?
Yeah, it will be a link to your talks, basically, to the program.
So if we just go to the conference website.
Yeah. And the sooner you send me your slides, the sooner it will be there.